Unit 1 of Intermediate Six Sigma. We're going to talk a lot about measuring now. To start off with measure, let's talk about lean, the lean glossary. Oh my, it's a whole new language. And there are many terms. These are the lean tools. These are are how you make yourself lean. Again, we're going to talk about value and things. The part that Six Sigma comes in, the part I'm going to focus on, and part of lean, is how do you measure lean success? How do you put a score on it? How do you see if it's really effective? And that's where Six Sigma links up with lean. We're going to look at the lean, see if we actually did make a difference. I've attached in the reading a lean glossary. Go through that. If there's one you don't understand or want more explanation on, go to discussions and bring it up. So we need to start thinking about lean. And WOMAC has 5 guiding principles: specify value by product. Why would the customer pay for this? And if you can't remember what value is, it's if benefits over costs, and your benefits have to outweigh your costs. Look at the little picture in this slide. And if you got competition, if they got more benefits, less costs than you, you're going to have issues, right? So you got to specify value by product. And we'll talk about value streaming later on, but basically if it doesn't have value, it doesn't need to flow. Don't let your waste flow through your process. In other words, make value flow. And the customer pulls the value. He's the one that decides what value is, okay? And he's the one who's going to pull it out of you. And if you attach a bunch of waste and muda to it, he's not going to pull a whole lot from you, right? And you got to believe perfection is possible. That's where Six Sigma comes in. Pursue perfection. Underpinning all of lean is this concept of value. Now, I don't know if I ever mentioned this, but the customer defines value. Benefits over costs. And you know, the big temptation of management is to cut costs while considering how cutting those costs will affect the benefits. They don't look at each product feature. Think of a restaurant. We have a local one here. They decided it's a chain restaurant. They started doing that heat and serve. It's a buffet. And instead of making the food fresh, disaster for the restaurant. In fact, it went out of business. And see if you can think of some more examples by yourself. Cultural view of value, it varies all over the world. And I'm going to pick on the Germans and Japanese here a bit. Germans, they value technology. Engineers run all the businesses over there, or generally run the businesses. And so that's a value. In fact, you go over there, and then a lot of times you'll see commercials, and you'll see a CEO saying, I am an engineer, I run whatever company. The Japanese, it's got to be value to the society, not to the individual. Society must benefit. There's a thing called the Taguchi loss function. I'm not going to go over it here, but take a look at it and see if it makes sense. Target cost. What you do is it's good old economics. Supply versus demand. You look at what your competitors are selling the same product, or similar products for. We take that price, subtract out all the muda, and that should be your target cost. So what you want to do is what's called value stream. You want value to flow through the process, the whatever you're doing to flow through there. And as you do that, it'll magnify the muda, the waste, but also magnify the value. 3 things you got to do. You got to solve problems. Fundamental. If you got a problem and it's interrupting the value stream, you got to fix it. Information's huge, right? So you want value. Information is value. So you want that to flow freely. Physical transformation. This is where you actually take a product and move it about from or change this form, shape, or function somehow. Again, value stream map is what we're going to talk about next. Value adds value as perceived by the customer. Notice I say perceived, right? And that will change quite a bit. If the customer thinks it's valuable, okay, that brand thing, not so much value to me, but some people will take the brand. They won't take generic. And if something adds no value but is required, you got to do it, right? You got to minimize that. And that changes from also, right? I'm going to go back to warranties and 100% tests. At one time, it was perceived that 100% inspection was good. That added value. So you had to do it. But as time goes on, people think, well, why do you have to do 100% inspection? The quality should be built in. Is your product so terrible that you have to add an inspection? So you can eliminate that, reduce that. Maybe do sample inspections. Eventually you get to where it adds no value, not required. We were making a product and they spent almost an hour putting a brush finish on this hydraulic valve. Looked good, and it was actually kind of cute. Sent it off to the customer. First thing he did is he painted that thing. So that patina that they put on, absolutely no value, not required. Eliminate 40 minutes of labor. Hey, that's a lot of money. Okay, let's talk about a value stream mapping. And there's going to be an example in the readings. But what a value stream map is how's the product flowing through your factory, or is a service, how's it thrown through your office? But basically what you want to know is the product development, customer requirements. That's where you'll find the value. The customer's telling you what he values. And how are you going to get that value to the customer? What's your method of delivery? And how much does he need, right? And then you want to do the process design. What you do is you walk through the process while recording everything, right? You want to start at the back, the shipping dock, where it leaves, and work backwards to receiving. And while you're doing that, you're looking at cycle times, machine times, operators, changeover times, WIP, available time, scrap downtime, etc. And I use a factory example, but this also works in a service type product. You want to record everything you find. Use a big piece of paper and a pencil. You're going to erase and take a stopwatch with you. You're going to have to record some times here. Take it back, look at it, and then get rid of the muda, and you plan your future state and map that out. That's a process map. So when you start thinking about lean, you want to get this thing called value flow and a couple concepts. Continuous versus batch flow. Traditionally we do things in batches, but if you can get it continuous, there's an advantage to that. I can't find a video, so I guess I'm going to have to shave and make one myself, but I'll show you the advantages of that. But basically what you want is you want a single piece, no work in progress. You want everything within reach, cellular sequence, right? And if you do that, you got more than one piece of person, you got a cross train, right? So you can go to the different stations. And it relies on absolutely zero breakdowns. You have a breakdown, you're pretty much screwed. So TPM becomes important. But it's all about eliminating the 7 mudas. And I'm using the manufacturing example, but if you can't see how it applies to the office, let me know. In fact, I'll give you an example. When I do these PowerPoints, I used to do like all the writing and the outline, everything on that before, then come back, insert the audio, and then I'll go back and add some readings, and then I'll go back and do some questions on the quiz that pertains to it. Now, as I go through, as soon as I'm done recording here, I'm going to go back and add the readings. And you can tell I don't get so tired by the end of the slides, right? So you do your value stream map, and you get the lead times down to hours, if not minutes, right? So what you want to do is you want to use this thing called pull value. I'm going to lean on Womack quite a bit from the 90s. Big thing about this is you make no forecast. Back when I was a product manager, they always asked me how much we're going to sell next year. And I'd have to make a forecast. Well, I didn't have any idea, right? And I asked other managers how they did it. They said, we don't have any idea. We just kind of guessed. Not the best way to do it, not the most accurate. You make too many, and guess what? We're stuck with a bunch of valves, right? Car makers used to do that. We used to get good deals when they got their forecast wrong. They made too many Monte Carlos or something, and we would come in and get them cheap. So what does Amazon do with their books? They make them as required. If you want the electronic version, man, it's right there in Kindle. Absolutely just download the book. If you want a paper copy, they don't print it. It's automatically hooked up to a big data bank, and you order it, it automatically triggers a book being published, right? And good things happen, okay? Cycle times go down. You don't have any inventory, no big inventory. Work in progress goes way down. Customer orders are stable. You know, back when I had an unreliable supplier, I'd order 2-3 months worth of stuff just because I didn't know if I was going to be able to get it. Customer orders are stable. Is a big thing for you have stable customers. You don't have those big spikes in orders. The price is also stable, right? You're not paying to keep the inventory. You're not having big sales to get rid of excess inventory. It's a much better system. And again, if you predict and you try to make, say you have 20,000 cars you got to sell, and there's a demand for 8,000. Oh man, you got to push it. And the way you do that is price, quality, or selection. Well, you got to get the price down. That's the only choice you have. Probably nowhere does Six Sigma directly tie to lean more than in perfection. It's all about being perfect. And what is perfection? Well, you specify value. And if you can deliver only value with no muda, that's a perfection. You want to enhance the value flow. You want to make that value flow through your processes to the customer, and the customer's the one that's going to pull that out of you, right? Pull it out of the organization. You want to achieve total pull, right? Absolutely no push on the customer. And you want to collaborate with your suppliers, your employees, customers to even find more value. What would be even more value to you? And the use of technology. The last car I bought it. One of the big selling points, I knew that it was built by robots, because I knew it would be built very, very exact, very, very, very precise. It'd be near perfection. And finally, you want to design for Six Sigma, make it possible to make these. You ever had to make something and it just weren't given the tools, weren't given the materials, weren't given the instructions, weren't given something. And you had to make it, right? And then after you get done with it, you had to cobble it together and make it work. Design for Six Sigma, you make something that, whether it's a process or the product or whatever, you make it so it can be achieved perfection. That's the ultimate goal for Design for Six Sigma. Make something that can be perfect. One of the key things to lean is takt time. How fast you have to make something, right? So takt time is simply the rate at which a finished product needs to be completed to meet the customer demand. This was originally developed, I think, in Germany. Takt means it's that little stick that a conductor holds up, the baton. In the 1930s, the Germans did it. So when the Japanese took over, they didn't have a word for rhythm, so they used the German word takt. So this actually came to us via Japan. But basically it's just production time divided by the customer demand rate. Or another way of putting it is available time divided by demand. Real simple concept. Take a look at this picture. I'm not going to talk about it. We got an issue here, right? Operation 30 and 20, they can't make it fast enough to keep up with the customer demand. We're going to have it. I'm going to put this in discussion. We'll talk about it. Okay, this is going to be one real quick slide. This is a takt time example. Widget factory operates 480 minutes per day. That's 8-hour day, 60 minutes in a day. Customers need 240 widgets per day. That's real easy. Look at your orders divided by days, right? So if you take 480 times 60, that's how many seconds there are in a day. Divided by the demand, 240, get 120 seconds or 2 minutes. Again, I like thinking in terms of seconds because it forces you to get more and more and more precise, more exact. I'm going to talk a little bit about some metrics, 3 big ones that I haven't discussed anywhere else. You know, we talked a little bit about the financial. We'll talk about TPM later on. But the throughput rate, that's equal to 1 divided by the cycle time. So if you know what the cycle time is, you can figure out the throughput rate just by dividing. Total lead time is a number in process. In other words, say WIP here, versus divided by the average completion rate. That's how much your lead time is to your delivered to your customer. Process cycle efficiency, value added time. You get that off the value stream map, and you divide that by the total lead time. And usually these are about 10-15%, very low usually for companies starting off. I'm not going to do any examples on these, but I'd like for you all to go back in Black Belts and research these a bit and see what you think of it. These are the three fundamental metrics, or not fundamental, three metrics that are used in Lean. I guess they are fundamental. Okay, we're going to talk about process analysis in terms of Lean. Again, we talked about the value stream map. Again, I encourage you to look at the videos on that. It'll take a while, but it's a very good tool. Flowchart we talked about in Greenbelt. ISO standards, in particular, on what I'm going to do in the reading is non-conforming material, the isolation. And it works also in the office. If you got some kind of a process, you make like waste, take a look at it, get it apart. You want to see some waste in the office, go at the copy machine, look in the waste basket, see how many bad copies there were. Work instructions, I'll give you an example in the readings. Spaghetti diagrams, pretty straightforward. I'll give you an example in the readings. Circle diagrams, there's a bunch of these. Pie charts, dial charts, risk management. All it is basically a way to keep score. And then you got the analysis, the plan, do, check, act. Designed for Six Sigma, has some circle charts. Take a look at it. I'm just going to leave that up to you all. Gemba walks. Gemba means work area. In the case of manufacturing, is of course this is the manufacturing floor. If you're in the office, it's walking around the office. And basically what happens is management gets down once a month or so and walks around the floor and looks for housekeeping opportunities, right? Be careful with this one. I've seen a couple people implement it. And management feels obliged to do some kind of change, whether it's good or bad, just make some kind of impact. If it ain't broke, don't fix it. But if it is broke, fix it. This is where Six Sigma can come in. If somebody makes a change, did it actually save the money? Did it increase efficiency? Did it increase quality? Gemba walks. And I'll find some readings for you. Two types of data, variable and attribute. And if you want to, you could throw in a qualitative, but with a Likert scale, what we do is we take that qualitative data and turn it into quantitative data. First one that I'd like to talk about is attribute. This is a very discrete. This means that data values can only be integers, 3, 48, 1056, whatever, but it's counted data. And it's like how many, how often, what kind, right? But you can't get a fraction out of that. Variable data is the other type, and this is continuous. This means we can have any real number or any kind of fraction. 1.28, negative 7.3789, 84.35. It's measured data. It's variable data. That answers the questions like how long, what volume, how much time, how far. And I've got this chart here. Take a moment, just look at it, and see if you can't tell the difference. Okay, I kind of lied. This is called locational data, or measles, making a measles chart. It's basically just another form of attribute data. And basically, this is the actual measles chart from Romania, where all the measles cases are. You can see that one area is concentrated very strongly. There's another little area that's got some more measles cases. In some places we don't have any measles. Again, it's attribute data, number of measles in each county or whatever it is. So the way you use this stuff, say you're an ice cream manufacturer and there's a salmonella outbreak, and then you start doing a measles chart, and all the dots are on top of your factory. That's going to be a bad day for you. So why do we need to know what kind of data we have? You want this chart, and what I'm going to do is I'm going to post it in the discussion. But the way this works, you take your input, let's say it's attribute data, the discrete data, and you get, say, a variable output. you can see what kind of statistical test we're going to do. Or let's say if it was a variable input, variable output, you can see the kind of test we're going to do, or technique. That's why it's so important. And this is also I don't want to scare you, but this is a clue of what's coming. Okay, there are 4 types of measurement scales, and they go from nominal, which is just basically data with names and categories only, through ordinal, which is so you got some kind of order, some kind of ranking, say position in a race or criticality, whatever you want to do it. Interval, which starts to be variable, it has a range in order and can be, and you can start looking for differences now, right? Ratios are meaningless in this point, but then you get into ratios that include an inherent 0 starting point, and that's the trick. You got to have that 0 starting point. And this could be like money's a big example. Anything that's going to be into a ratio. Okay, we got different types of sampling. We got first type, of course, is random sampling. Every member of the population has an equal chance of being polled and studied. That's the definition of random, and we pretty much have a good feel for what that is. Sequential sampling, that's kind of different. And the only example I could probably think of is like in Flint when they had the lead in the water. Well, what they would do is they take a sample, right? Oh man, we got way too much lead. Then they take another sample. Ooh, it's coming down, but it's still a good probability that we got too much lead. You keep on taking sample after sample after sample and after sample until you're pretty sure that there's no lead in the water. Stratified, this is where you take like different lots, different batches, different offices, different departments, whatever you're measuring. You take the data from each one of those and you can compare them to each other. And some of the dangers and rules, right? Emotional bias. You know, if I take a part out to somebody on a factory floor and say, hey, what's the diameter of this widget? First thing they'll ask me is, what's it supposed to be? And they'll take their gauge and they'll kind of push on it if it has to be smaller, or let it be very loose if it's not big enough. That's bias. The other thing you want to be careful of is rounding. There was actually a spacecraft crashed into Mars pole because they rounded off when they converted from metric to inches, or inches back to metric. Be careful of that. It'll cause some error. Out of sequence, if you get something out of sequence, again, this is all about control charts, right? You want to keep it in sequence. You're looking for trends, right? You can't do that. If characteristic changes, dimension or something, you want to be able to catch that. Statistics, you assume normal population, and I throw it at you, black belts. What's my tool to determine if I've got normal distribution? Okay, what is my tool I use to check for normal distribution? You could miss errors. You're not sampling frequently enough, and you might miss important information. Again, this is a frequency type thing. Okay, so you got this problem. You know what the problem is. You need some data to analyze it. So you go out and you collect the data. First, there's different methods. Automatic, which is by far my favorite. You basically just get a computer or something out there and they take the data automatically. No human involvement. Coding, this we use a lot in qualitative data. Basically you take like a Likert scale, you convert it into quantitative data, and so you can analyze it. I'll have a link in the readings to talk about that. A check sheet, that's basically a tally. You have somebody out there making little tick marks every time they do something or find something, whatever it is. Close to that, another form is a checklist, a grocery list. Basically, this is something that somebody might follow to make sure they do something. We can go out there and you could check that, see what they missed on their grocery list. It's very rare when you don't have to collect data, but every once in a while you'll run right into it. You'll find this in the medical field quite a bit. There are certain things like if somebody comes in with a stroke, you got 20 minutes to give them the medicine. They have to keep track of that. You can go actually analyze that. You can look at medical records and find out why somebody died. That's the nice thing about hospitals. There's a lot of data, not much analysis. Measurement system analysis. Oh, this is like a 4-hour class. And I will come in on a live session if enough people are interested and discuss this. Two things we're worried about is repeatability and reproducibility. Repeatability, can the operator or the guy taking the measurement get the same measurement over and over and over again? Reproducibility, can somebody, a different operator, get the same results over and over again? Is there a correlation between the operators? We're going to use the analysis of variance method. Where's this coming from? Is it from operator to operator? Is it measurement to measurement? Or is it part to part like we hope it is? The old way was all done with control charts and ranges, but we're going to use ANOVA in this class. 5 types of errors. Bias, how much does the gauge vary from the true value? Repeatability, we talked about reproducibility. Stability, is the measuring system, is it give the same results again and again under different conditions? In other words, can I trust it from day to day? Linearity, I've got a refrigerator thermometer. It goes up to 80 degrees. I take it out and I try to measure the outside temperature. It's 102. I got a linearity problem. I can't take it beyond the range of 80 degrees with any certainty. That's what linearity is. A couple metrics you want to know. The precision to tolerance, which is basically 6 sigma divided by my total tolerance. And then they got precision to total variation, which is 6 sigma of the gauge to the total variation in the entire system. Enterprise, everything has a metric, there's the obvious ones, thermometers, sigmometers, rulers, but everything else could have a metric too, whether it's accounting or purchasing or administration. Everything has a metric, and the science of measuring things is called metrology, and it's really quite a science, very interesting. I won't get into it. Make sure your units, you want to be careful of round off. And the total variation that you see is equal to the variance total is equal to the variance of the process plus the variance in the measurement. You want the measurement variance to be about 10% or less by rule of thumb. And I'll leave it up to you to figure out why I'm using variance and not standard deviation in this equation. We talked about measurement error. Calibration, this is kind of interesting. What we can do is any gauge you have, if it's been calibrated under the ISO standard, right, you can trace that calibration of whatever gauge you're using on the floor or in the hospital or whatever, up through another calibration to another calibration, up to the NIST standards, and NIST can trace theirs back into Paris. And there's ways to get around that. If you got a lot of error, but it is calibrated, you can use the central limit theorem. And I'll probably use that as one of the quiz questions. But see if you can figure out why you need a central limit theorem. If you're calibrated, why it will work. Okay, we'll see you in the quiz and discussion part and the readings.